Session is going to be on big data challenges in energy and the environment. We've got two speakers lined up. First up we have Andrew Richards talking about future challenges for scaling big data at the National Grid.
Thank you very much for inviting me here. My name's Andrew Richards. I'm sort of a mathematician rather than an engineer working at National Grid. National Grid's a big sort of company working both in the US and the UK. We work in transporting energy around the place, primarily gas and electricity. I work entirely in the UK on electricity, and I work at the Electricity National Control Centre, where we operate the system for Great Britain, because Northern Ireland, for the purposes of energy, belongs on the island of Ireland. National Grid's electricity network is the high voltage network. High voltage typically means 200,000 volts and above, although it's slightly lower in Scotland. There's, I think in Scotland we go down to 132,000 volts. There's almost 8,000 kilometres of lines and cables that we look after. We have, roughly speaking, 1,500 high voltage transformers for changing the voltage from the 400,000 volts, which is the highest we use, so that doesn't actually have to go into your house and you don't have to plug your kettle into 400,000 volts, which is a good thing. We have 400 nodes on our network that we maintain. A node, although it's represented by, that's clearly the wrong thing to have pressed there. Let's get back there. A node, which is one of these little dots here, is typically 6 or up to 10 very large supergrid transformers, each transformer about the size of a 2 up, 2 down house, with a lot of supporting equipment around it, a lot of switches so that we can control the way the electricity flows. It's really a big boys or girls toy. The engineers love it. That means that each of those dots is actually very complicated in real life, and we have an awful lot of remote monitoring so that the control engineers in the single control room can understand what is happening on the grid, adapt to it in real time, and also plan safely for the operation of the system into the future. To collect all that information, we have about 420,000 different bits of data that come in. Some come in at secondly level, every second, some come in every minute. There's about 60 million updates of data a day. And in my sort of terminology, I consider this to be large data. We have to manage it quite carefully, but I don't yet think that this is big data. And I'll explain in my mind what the difference between large data and big data is, because I don't think National Grid has hit big data yet, and what I want us to be is ready when we do hit it. This is a representation of the electricity network. Instead of as a map, as a sort of London Underground diagram, the engineers call it the Picasso. And it shows all the electrical properties that the engineers are working on, as well as some interesting sort of red squiggly lines that get drawn on. Those are usually boundaries that we are worried about on a particular day, so they're drawn in with a little sort of laser pen or something on the screen. And what we're worried about is flow of energy from one side of the red squiggly line to the other side of the squiggly line, and we have to control it. That might mean that we have to reduce power on one side of the line and increase it on the other side. We make a big distinction between transmission and distribution of electricity. This is kind of the old view of what used to happen. We had generation, which is owned by independent generating companies. National Grid picks it up at a transformer, and then all those large big pylons you see around the place transport that maybe through a cable down to another transformer where it gets down to 132,000 or 30,000 volts on much smaller little pylon lines, which is called the distribution network, and then down further and down further until it comes into your house at around about 240 volts. So we do this bit, which is the very high voltage bit, and then it's split down into the distribution, which is the lower voltage bit of the network, which goes directly into houses and factories. We have a legal obligation to make sure that as far as is possible, we supply power at all times on the transmission network, and our reliability is very, very good. That unfortunately doesn't mean that the reliability of electricity going into your house is as good, because our lines up here are at least sort of 30 or 50 meters up in the air, supported on very large pylons. But down here in the transmission network, they're supported on little cables. If a tree falls over here, it tends to fall over underneath our lines. If a tree falls over here, it can go through a line and can disconnect you. It's also much easier for somebody working on a road to drill through a power cable here. It would take some ingenuity for a road worker to drill through a cable up there. That means that the distribution network is not as reliable as the transmission network. But when a bit of the distribution network fails, you might lose electricity to a street, you might lose it to a town. It would be bad. If we lose our reliability at one of our main transformers, then we could say disconnect Birmingham, Leeds and Liverpool or something. So our failures, although they're very rare, if they do occur, have much more impact on a far larger number of people than a distribution failure, which is why we're so keen to keep this figure as high as we possibly can. Unfortunately, the system doesn't look like that anymore. It's no longer just a question of generation somewhere in the remote wilds of the country, feeding huge pylons and then coming down into people's houses. It's now much more like this. We've got some large power stations. Here's the high voltage network. Some heavy industry which may connect directly to the high voltage network. We come down here and we get into the low voltage network, the distribution network, where there may be solar panels, there may be distributed microgeneration, light industry may be actually having its own generation which it can pump back into the network. It's no longer a one-way flow of energy from big power stations down to the end consumer. Everything has become much, much, much more complicated down here in the distribution network. So much so that the distribution network, it can actually be now, bits of it can be generating more power than it requires, so it can become an exporter onto our transmission network. And we have to be able to model all this, cope with it and plan for it. And there is an added complication from my point of view, which is that in the UK, no generator in England and Wales that is below 100 megawatts has to provide any data at all to National Grid as the system operator. So if you are a large nuclear plant or a large gas plant or a large coal plant, you have to tell us a day ahead what you're planning to do. You have to tell us 4 hours ahead what your final position is. You also have to provide us with real-time metering so we can see what happens. But down here, you can have generators which are 99 megawatts, and I kid you not, there are generators of 99 megawatts because it's much cheaper not to have to provide all this information than it is to actually provide it. And those things, they can be large, there can be an awful lot of them, and they can be generating. We have no idea how much they're going to generate on a given day. We don't know whether they're running or not. No plans, no outturns. Outturn is a word we use a lot. It just means what happened. So there is no single solar power farm which is over 100 megawatts, so we get no data about solar power. at all in the country. Wind farms, there are a lot of wind farms which are over 100 megawatts, but there are also a lot of wind farms which are below 100 megawatts. All this stuff, which is very variable, we get no idea of what they think they're going to do on a given day. We don't know if they're operational. They may have broken down. They may be doing repairs. It leads to a lot of uncertainty on our network. Even on the bit where we do receive data, either from the generators themselves or from metering our own data, trying to find out what's actually happening on the system at any given time. That horrible thing there represents the data flows of all the data that is coming into the company about electricity, not about sort of finance and all the rest of it. This is just the electrical information about electrical properties on the network at any given time through lots of different, lordy lord, I haven't done it again. Lots and lots of data systems flowing into lots and lots of databases, all of which connect in an absolutely hideous way. We're stuck with this historically, the way that the system has grown up. There's no single repository of information. We're just trying to make sense of this huge flow of information to understand what's happening now, what did happen in the past, and what will probably happen in the future. It's really quite a complicated business. Real-time data flows, of course, are driven by things like this. I couldn't possibly wire one of those. I just do not understand how such a thing operates and how anybody manages to get all the right things plugged into all the right other things. This all gets drilled down into loads and loads of screens of information like this, which the operators read and understand. This then feeds them into understanding their sort of little specific bit of the diagram. So you'll have an operator who'll be working on a small bit of the network, making sure that it's electrically stable. And this is a photograph of the inside of the control room with our big control board that flashes red if there are any critical issues on it that you need to take notice of. So basically, from my point of view, it's probably more complicated than I think it is. It is pretty horrible. But we do need to understand what's going on in real time. These are just some of the reasons why we need to do this. There are lots of different reasons, but this is some of them. We have to make sure that generation meets demand on a second-by-second basis. If generation exceeds demand, then what happens is the generators themselves, the big generators running, find it too easy to operate. There's not enough resistance on the network. They spin too fast, and there is a tolerance. They're supposed to spin at 50 hertz. If they spin at more than 50.5, they'll start to shake and rattle. Round about 52, they'll probably come off their bearings. It's never happened in the UK, but it has happened elsewhere in the world, and what you find is you get a great big turbine, which is probably twice the length of this room, a big solid chunk of spinning metal, which will fly up into the air, go through the roof of the turbine hall, shatter into large chunks and scatter itself around the generator for a distance of up to 1 kilometre. This is not good. If, on the other hand, generation is below demand, it's like trying to drive a car up a hill in the wrong gear before the days of automatics. The machines struggle to turn because the resistance is too great, and eventually one of them will stall. Immediately one stalls, then of course the disparity between generation and demand grows, so another one stalls, and you get a catastrophic collapse, and you could get a national blackout. So imbalance causes frequency deviations. We have about 10 seconds to arrest a large frequency deviation swing before it becomes uncontrollable. Automatic things ought to kick in after about half a second, so there are automatic generators on the system, but operators will need to take action immediately they see a very large frequency deviation either up or down, in order to ensure that nothing happens like an exploding generator or a national blackout. So we do not have very long, therefore we need accurate information. We're transporting large amounts of power around the place. As you shove power down an electric wire, it heats up. If it heats up too much, then it starts to sag. And you'll be walking down a road and a sagging line will come near your head, and that again is not good. So we have very strict provisions on how much power we can send down a line. That's why we have those red squiggly lines. We want to make sure that we know how much power is there. We have limits about how much, we know exactly how much each line can take. If it turns out that there's too much generation on one side and not enough demand, electrical laws will just make that power go down the line. We have to reduce the amount of power on one side, and then we have to replace it on the other side of the boundary. Too much power, heating, expansion, sagging of power lines. We also need the network to be dynamically stable. Basically, you've got lots of spinning machines which are connected by electromagnetic signals that go down the power lines. So they all spin essentially at the same rate. We say they all spin at 50 hertz and they all spin exactly in time. They don't. There are slight sort of variations as the amount of fuel going in isn't quite smooth. So one machine will slightly speed up and then slow down again. And the whole thing works, so it's like they're connected by a very stiff rubber band. And you need to make sure that they all effectively are turning at 50 hertz, even though there are small variations. If you don't have what's called enough inertia on the system, and this is electrical inertia, which is generated by the actual spinning metal of the turbines, you get physical inertia converted into electrical inertia. Then you can have machines that speed up. Another machine in a distant part of the country will sense that, it will speed up. By that time this one will be slowing down, and then you can get oscillations between different bits of the countries, and those oscillations can grow with positive feedback, and that rattles the bearings on which the turbines sit and significantly shortens the lifetime of the power station. So we have to make sure that we do get this stability here. So that's instability causes generator turbines to swing, can cause damage or even catastrophic destruction. We also, and this is one of the really big things we do, we have this enormously successful reliability rate. We have it because we say the system must be able to withstand 2 simultaneous credible losses. So essentially what you would say, if you were planning the system for tomorrow, you'd say, okay, what's my largest single credible loss? And that'll be the Sizewell B nuclear power station at 1,260 megawatts. You'll then take something else, which will be either another large power station, or you'll say maybe it'll be one of the main lines that carries the power around the country. We would say must be able to withstand that line falling. So 2 things independently failing, the system must still be able to operate with that. 3 things fail, then we run into trouble. But 2 things failing simultaneously, the system can cope with for a short period of time, which means about 4 hours, while you recover the system and you resecure it so that it can be ready for the next loss. So an awful lot of our work is involved, I'm not very good at this, is involved in making sure that if there is a fault, the system will remain secure. All of this requires very, very detailed knowledge of exactly what's happening, delivered to us as rapidly as we can. Now we have all those data points around the country. A single node probably has round about 1,000 data points feeding us. No, that's wrong. No, probably about 400 data points feeding us. So we get 400 data points per node. Some of the bits of information are wrong. Some are contradictory. Every now and again we find that we've got a bit of information and somehow the meter that's feeding it has been checked, somebody's come along, serviced it, and they put something back in the wrong way round, so we're getting a negative signal instead of a positive signal. Because we have all this contradictory information, we have something called the state estimator. Now, we are estimating here the state of a network, but it's rather different from estimating the network that we heard about this morning, because here we're not estimating the topology of the network, which we know about. The topology is given. We're trying to say the information we've got on the network is contradictory. What's our best way of resolving this so we can get a best view of the system? We have this state estimator. It's partly automatic, it's partly manual, because we dress some of the data that is apparently wrong. If it remains wrong for more than about 10 minutes, then somebody goes and they look at it on the computer screen and they say, oh, I can see what's wrong here, and they may either remove it or they may adjust it in some sort of way. But there are a lot of sort of mathematical algorithms going around, and they tend to be sort of a recursive attempt to try and understand what the state of the system is. So this state estimator has been running. It took about 8 years to get it to work as well as they want, and finally around about 2012 they were happy with it, and it's been running very, very happily ever since. But it was a complicated thing to try and resolve all the different bits of information that it was getting into the best view we could get of the system. Right, planning for contingencies. This is planning to make sure that if there is a fault, we can recover from it. If there's a shortfall of generation for some reason, that might be because Sizewell B breaks down, but it might be because out of our fleet of wind farms, which may be producing 8,600 megawatts of generation on a given day, the wind isn't quite as strong as the Met Office said it would be, and so you get much less generation. It may be that our PV generation, which although we don't, sorry, that's the solar generation, solar PV, it's the same thing. Although we don't get any metering for it, we nonetheless model it as best we can. On a day like today, PV generation is a hard thing to model because you get lots of snow falling on top of solar panels. You don't know exactly how much is settling on the solar panels, and that interferes with the amount of solar generation there is in a way that is very hard to quantify. But what do we need to do? We need to forecast the demand at national level and also at the level of all those nodes which either bring power onto the system or take power off the system. We need to forecast how much conventional generation there is. We're notified of this, so it's not too hard to forecast, but we also have to take into account the probability that it might fail. We've got the renewable wind and solar generation. That's dependent on the weather forecasting accuracy and other things like the snow. Other generation, which is connected to the distribution network, which is below 100 megawatts, and we get no information about it at all. Basically, we use mean levels, average levels of distributed generation because we've got nothing else to work on, and it seems to work at the moment. This generation, which we receive no information on, we don't receive either forecast information or outturn information, so we don't know what it was doing and we don't know what it's likely to do, and it can make up to 30% of the total national demand. So we cope quite well with this uncertainty, but this is growing rapidly. This is growing rapidly. There are other things happening on the electrical network. Electric vehicles, changing use of technology, heat pumps, conversion from gas heating to electric heating, which hasn't happened yet, but the government is trying to drive forward in the future. It's part of the energy policy it has to convert from gas to electricity. What else have we got? We've got the possibility that we might have, say, price-sensitive information about wholesale prices and how much it costs the generators to generate and scarcity pricing on the network. So you find that if we're running a bit short of electricity, as we may do tomorrow evening when the demand is forecast to be significantly higher than it is either on Monday, Tuesday or today, from 47 megawatts tonight to 49 megawatts tomorrow night. That gap has to be filled. That means that there will be much less spare generation around. It means the price will spike. There are suggestions that those price spikes get fed through smart meters into your homes so that it can encourage you not to use electricity when it's short. Now, you may not like the idea of that, but I like it even less than you, because it means that in order to forecast accurately what is going to happen, I have to be able to forecast not only the demand, the generation, anything that could go wrong, the reaction of the financial markets in terms of wholesale prices to those things going wrong, and then your reluctance to reduce your demand. You may be happy to do it, but you may have a big dinner party, or you may be preparing for some great event that means that you really do need to use your electricity. All this will just add more uncertainty. So we're trying to reduce the uncertainty, but we have got these increases in the amount of renewable generation. We've got this more active management of distribution networks that the government is trying to encourage. We've got new technologies, some of which I think I mentioned all those already. That gives us more uncertainty. And when there is uncertainty, it is more expensive to operate the system. And if it's more expensive to operate the system, that means that the customer has to pay more. The easiest way to reduce the uncertainty is to increase the amount of information we get. So there's talk of electric vehicle charging. The people within the grid who are responsible for electric vehicle charging think that National Grid would be a good national repository for every single electric vehicle charging signal to be fed into us, and just to save it there in a nice big database so we can use it for forecasting, outturn and understand what's going on. Now, in my view, that will be big data. If we have to receive real-time live data about electric vehicle charging, then that is massively bigger than anything we do at the moment. And my concern is that we don't know how to deal with that. I don't know the mathematical techniques that I use at the moment, standard statistical linear modeling, time series modeling, nonlinear recursion. We use a certain amount of AI, decision trees, random forest regressions, those sorts of things. I do not know how many of these techniques will continue to work in the time which they would need to work in, so that we can get a reliable understanding of what's happening on the system, so that we can stop any of the disasters that I've been talking about from happening. I simply don't know at the moment. So what I know is that I do not know about scalability of these methods. At the moment we're fine. We can do all this, but in the future I very much suspect that there will things that we can do now that we will not be able to do in the future. And that is effectively my pitch, that we're in a position where we use a lot of data and we can cope. But if we move to a world where we seriously do have large data, big data, and my definition of big data is you're now getting enough data that the methods that used to work don't work anymore. So as long as my methods are working, I don't think I've got big data. Immediately they stop working, I think I have. And we need help, I think. Thank you very much.
I'm particularly interested, I work on some energy projects, I'm particularly interested in the interface between the technical side of the modeling and the economic and social. So do you Do you have I know at Atomic Energy they have like the engineers in one room and the economists in the other one, and they're doing supply and demand, and they tell the engineers what to do every half hour or so. I mean, do you see a future in which the economic side and the technical side works more closely together?
The economists tend to use sort of their large-scale models, and I apologise if I offend anybody, but in my experience, economists tend to work with models that use average values. They use mean values all the time. They don't take into account fluctuations. And that is absolutely fine when you are planning what's going to happen 2, 3, 4 years down the road.
If you're actually buying electricity in the next half hour from Norway or something, don't you have to have?
So we have traders who do that.
So the trading models talk to the.
Yes. So the traders will go in to talk to the control engineer, the power systems manager. He'll say, I'm worried about this period here because the demand is here, the generation is here. I want to carry an extra reserve of this amount as contingency in case something happens. My screens are showing me that economically the best thing I can do is use this power station and this power station. Is there anything you can do to get on the phone and do some trading and get something cheaper? And they'll look at it and they'll say, well, I think I can. And they'll go back, they'll ring somebody up in Norway, as you say, and either we can get some power or we can't.
Any more questions?
If instead of doing the vastly complex prediction problem that you try and use to help you out, you just gave up and said, here's how much the fluctuations are over the course of a day, a month, a year, in some fairly simple, relatively simple, just descriptive statistics, and then set the system up to cope within those to a once in 100-year level of failure or something. Why not do that? That's the question.
It would be enormously expensive to do that. The amount of fluctuation you get on a daily basis, if you weren't to take anything into account, you were just saying how much fluctuation could there be on a day like this, you'd probably be talking about plus or minus 10 gigawatts, which means plus or minus 10 nuclear power stations. That would probably cost,
What is the percentage of the
I don't know, 100. My guess would be about £500 million a day, which would then have to be shared out between the customers in the country. Would be phenomenally expensive. So it's an economic argument. It's not worth doing that. It's much better to reduce that plus or minus 10,000 megawatt thing to what we typically would get, which using the modelling plus or minus 600 megawatts. So tomorrow night we're forecasting 1st of March 49 gigawatts, so call it 50,000 megawatts. We can get that to within plus or minus 500. So it's 1% accuracy, and that 1% accuracy allows us to ensure that the contingency we hold is economically realistic and viable.
There'll be more time for questions and discussion at the end, so we keep the timetable. I thank Andrew once again.